First of all, I would like to thank the organizers for inviting me. I come from a very different background. I'm a computer scientist and a machine learner. And tools from probability statistics, random matrix theory, to understand machine learning algorithms. So that's my main role. And mainly because I come from a computer science background, it can happen that the language of this presentation is a bit different from a standard math talk. Particularly, I toned down on the math part and tried to replace the math with pictures. Okay, so the title of the talk, as it suggests, what we want to do here is do hypothesis testing for graphs, and what we want to really understand is when is this problem solvable in some sense, because practically it can be a slightly tricky problem to understand why it should be even solvable. So, okay, I think everyone here would know what hypothesis testing is. It's basically we have two conflicting hypotheses and we use observed data to test which is the correct one. I'll mainly talk about the two sample version where we want to test whether two sets of population come from the same distribution or not. But why do we want to do hypothesis testing for networks or graphs in particular? This can we reduce the structural assumption that we make? Can we keep it still a bit general? We would need to have some assumption to give some mathematical solution, but can we keep it still general enough? And regarding graph properties or statistics, characterized by another symmetric matrix Q. And as I said, we would want to look at the problem where the number of observations that we make, M, is way smaller than the number of nodes that we have. So we have large matrices, but very few observations. In fact, M could be even 1. And the question is, can we even consistently distinguish between the two models? And now we have reached the hypothesis that either P is equal to Q, that is the models are equal, or with respect to some distance, the models are at least at a distance of rho. I'll specify the distance later. So after a few slides, I'll talk a bit about the theory, but the main question is, given that we have a small sample size, can we solve this problem? And my answer, I'll give the answer up front, is that yes, we can solve the problem, because I'll present a couple of tests, show some numerical results which really say that we can solve the problem. So here is one test which works even when we have one observation. And so what we have is, it extends to more than one observation as well. So what we have is two graphs, G and H. We observe their adjacency matrices, AG and AH. And since we are working in this situation where we have a common set of vertices, all we have to do is just compare the adjacency matrices. The question is in what aspect should we compare them? So this test statistic is based on the spectral norm. We take the difference of the two adjacency matrices, rescale all the entries. This rescaling is basically dependent on a work by Laszlo Ardas, which says that you rescale it in a way so that the variance in total variance in each of the row adds up to 1. And in practice, there could be approximately, this rescaling can be computed just from the graph. So you rescale this difference matrix and then take the spectral norm of the difference matrix. And what can be shown is that under the edge independence assumption, but under no other structural assumption on the parameter matrix, asymptotically as the graph size grows, if the two models were identical, then this test statistic is something similar to a Tracy-Widom distribution. I'm being a bit loose here because we are taking the spectral norm and not just the extreme eigenvalues. So, but one can still relate it to the Tracy-Widom distribution by taking some union bounds. Whereas if the models are significantly different, I'll specify what that means, then the test statistic goes to infinity. So this gives us a very simple test. You compute this test statistic and you reject the null hypothesis when the test statistic is large enough. So, and well, this does not, I mean, except the edge independence, there is no structural assumption. I would want to stress on that. So, I mean, that's a crucial factor, but there is no other structural assumption that we would want. And what I would like to show is some nice pictures and the fact that it works in practice. So what we do is we take some, generate some networks. These networks are basically generated from the autocorrelation matrix of EEG snapshots. And we had a large number of samples, so we subsample from them, and in each run we computed six networks, 2 of each type. So there are 2 networks which correspond to epileptic seizure. There are another 2 networks which correspond to non-epileptic scenario, but the patient's eyes were open. In another case, there is no seizure and the patient's eyes were closed. And we do it multiple times, and what we do is, in each run, we do a pairwise comparison of all 6 networks. And what we find is that, what I report here is the test power, which basically means the fraction of percentage of times that the test detects that the 2 models are different. What we find is that 100% of the times the test shows, it distinguishes between an epileptic and a non-epileptic network. 70% of the times it distinguishes between the 2 non-epileptic networks. Whereas if we feed the same kind of model, so this is when we compare these 2 networks, this network and this network, both are of the same type, then the rejection rate is 3%, which is 5% is our threshold is the significance level that we set. Similarly here, the only difference that happens is the test still detects the 2 different epileptic networks very differently. Probably this signifies that epilepsy is a erratic behavior that one would observe. Okay, so and in this scenario, well, the networks were not really this inhomogeneous Erdős-Srény or even edge independent because they are from autocorrelation, thresholded autocorrelation matrices. So they work in practice. There is another test that one can create, and I won't go into the test much. The main thing that I want to say here is that this test works only when we observe at least 2 observations from each distribution. So we can observe, even if we observe more than 2, it works. And what the test statistic does is, it tries to get an unbiased estimator of the squared Frobenius norm difference between the 2 parameter matrices. So the previous one was based on the spectral norm. This is more of a Frobenius norm based test. And well, we can again assume edge independence and do some asymptotic analysis to see how the test statistics should behave in the null model. And that gives us another test. I'm just not going into that. And one can also use this test in practice. We used it on some real networks for which it's known. These are networks generated from some routers, about how routers interact with one another. And some qualitative analysis was known for this. What we did was we provided more quantitative analysis of quantitative versions of the observations that were known about these kind of networks. And also skipping this slide and moving straight into the theory as to what we want to understand in this scenario. So the main question that we would want to ask is, when can we test between two graphs? The problem that we would like to answer is whether the test that we have that is accurate enough, accurate in a worst case sense, that is given to arbitrary models, is its error rate still low? And at the same time, if there exists such a test which can solve the problem with a low risk, lower error rate. Okay, and this is where it's not a completely new approach, but it's a bit different from what people do in machine learning or learning theory in general. And that's the sample complexity view. That's the traditional way of looking at a learning problem, is to, you have a problem, how many independent observations do you need to solve that problem? That's the traditional view, which we don't want to take, because we have this limitation that we would want to solve the problem with a fixed sample size, or with some sample size, say m equal to 1 or m equal to 5. So we go into a more minimax testing perspective as to, we fix the sample size and then ask the question as what is the minimum difference that we can detect? That's where the significant difference comes in. And also, can we come up with an optimal test? Optimal in the sense that whenever we have the smallest detectable difference, can our test detect that difference? And these are all up to constants. Okay, by the way, I didn't mention, but these papers all the papers are on arXiv. I forgot to put the archive number here. So that's the main theory that we are going to look at. So just going back at the model that we had a common set of n vertices, the inhomogeneous Erdős-Srény models. I'll additionally make an assumption that the networks are sparse, in the sense that the maximum probability that we can have is at most delta. This really helps in making the results a bit neater. Again, we have the m observations from each of the models, and we want to test the hypothesis whether p is equal to q, or with respect to some distance. I'll specify the distance a bit in the next slide. Whether the two models are separated at least by a distance of rho. And the question is, why do we care about the distance? The fact is that we should care about the distance, or what particular distance we use, because every test that one comes up with, that test tries to use a particular kind of distance. So the distance really characterizes what test is being used. And it gives some pretty interesting results in when we restrict the sample size. So here are the results, which this is the notation of the results in colors. So what we do is we fix the graph size, that is the number of vertices. We fix the sample size. We fix the edge densities, that is the maximum edge probability that one can have. And we fix the distance function, where I'll choose some specific distance functions. And what we would have is, we would keep varying this minimum separation rho, and there would be different regimes that one can get. If rho is too small, then there are pairs of models which cannot be detected. So any possible test that we have is going to give a very high worst case error. So that would be this impossible regime, which is given in red, and this happens if the rho is said to be smaller than rho detect. On the other hand, if rho is set to be large enough, larger than this quantity rho hour, then what we are going to show is that our test works. So we would have this blue region where the problem is solvable and our test would work. And if the analysis, yeah.
So is this rho detect something which is intrinsic to the problem?
Yes.
And it can be computed?
Yes,
okay.
That's the question. In terms of the minimax separation, the rho detect is the lower bound on the minimax separation. Whereas rho hour is test specific, so rho hour would be an upper bound on the minimax separation. And if they don't match, there will be a black region where we don't know. And what I'll try to show is that we don't have a black region. That's the gap we bridge. And that would in turn mean that the tests are also optimal in terms of in a minimax sense. Okay, so what if we take the distance to be the total variation distance? That's the standard thing one would take in a hypothesis testing context. So take the distance to be the total variation distance between the two probability distributions that we get. And what really happens is, oh, by the way, the total variation distance is what one would end up with if the test uses some kind of a chi-square test statistic. There are variants of chi-square type tests, and which are also used in the context of testing between graphs, and they end up having they eventually use the distance to be as a proxy for the total variation distance. That's the best way to put it, I think. And what really happens is, if the sample size is much smaller than the graph size, when we are in the sublinear regime, then everything is in the red region. So we cannot essentially have a test which has a small worst case risk. And there are a lot of tests used in practice which are used in this situation as well. So the total variation distance is not a good distance if we are talking about small sample problems. What about some other distances, say the Kullback-Leibler divergence? And what we also showed, and I just didn't put it here, is that again, if M is, I think in Kullback-Leibler divergence, it's sublogarithmic. Also depends on the sparsity of the graphs. If it's sublogarithmic, then it's again the same type of situation, that the problem is essentially not solved.
Could you please remind us briefly about the total variation of the definition?
The total variation distance is basically an L1 distance between all the point masses.
Okay.
And I particularly, the total variation distance is particularly also used a lot in the high-dimensional discrete distribution testing. Okay, but we had a couple of tests, and I showed that they work in practice. And here I deviate a bit from those tests which use asymptotic distribution. So here the analysis is more the test with asymptotic distributions use slightly stronger conditions. The optimal ones are tests which use similar kind of test statistics, but mainly rely on concentration inequality. So what if we take the distance to be the Frobenius norm between the two parameter matrices? Well, it turns out that if m is equal to 1, that is, we have one observation from each model, again the whole region is red. So there cannot be a test which has a low worst case risk. Whereas the moment we have at least two observations, there is a nice phase transition. These are equal up to constants. I really don't care about constants so much. So if rho is small, we have this impossible region, but the moment it crosses this threshold, the threshold depends on the graph size and the sparsity and also the number of samples that we observe. The moment we cross this threshold, our test works.
So that's the n delta is the number of different elements, right?
Delta is the maximum possibility.
Maximum probability. Well, if you assume
if it's uniform,
roughly,
we have
if you have a uniform thing, it's a number of different, on average, the number of different elements in this in each row.
In each row, yes.
Okay.
So it's sort of, you can think of it as the average degree.
Yeah.
Or n delta would be the maximum
Square of the-
average
yeah,
degree.
yeah.
Okay. So
Sorry, when would the square root of n delta over m ever be bigger than n delta?
if m is too small.
But m is more.
There are two situations. One is, it's better to say in terms of delta. If delta is too small, that is, if we observe an ultra-sparse graph, then essentially the problem should not be solvable because we don't have enough observation. And then, the maximum possible value the Frobenius norm distance can take is also n delta. So it's, we get the red region in the whole thing. But the moment delta is a bit larger, and that depends on the number of nodes as well as the sample size. If we have a large number of samples, say m goes to infinity, we get everything to be the blue region. So that's okay. So that's before I go further. So, and I mentioned when I spoke about the test which uses Frobenius norm difference, I mentioned that the test needs at least two observations. And the reason it needs at least two observations is because the problem is not even solvable with one observation. So we have to choose the distance carefully. If we just want to compare between two graphs, we have to be very careful about what is the distance we choose. And the nice distance turns out to be spectral norm. And what we observe is that if we have spectral norm as the distance between the two parameter matrices, then we have the same trend as before, but it works for all sample sizes, even for unit sample size. And our test is optimal in this way. Okay. Okay, so the proofs for this is not really complicated. They mainly use matrix concentration or some other concentration inequalities, and they work. But I'll just give a broad overview of the proof idea, and this will also help in generalizing it to the next step, where the graphs are not even on a common set of vertices. So the problem that we have is we have this two models, the parameter matrices, and that's what we want to compare. But what we actually end up comparing are the two adjacency matrices. And everything still works because, well, the adjacency matrices is a subset of the larger set of all possible parameter matrices. So they lie in a nice metric space. And because of that, what we can just use concentration of these adjacency matrices around these parameter matrices. So in the solvable regime where our test works, what we would have is with respect to some norm, the spectral norm or some other norm in different contexts, these distances are small. That's matrix concentration, and that's why if we have to detect the difference between P and Q, we can check for the difference between the two adjacency matrices. That's how everything works. In the impossible regime, we just use standard methods which people in Minimax literature use, where in our context it would really mean that on one hand we have an Erdős-Srény model, and on the other hand we say we have some planted model, say a stochastic block model, and if the perturbation is too small between the two models, they are essentially indistinguishable. They would generate same kind of graphs. So that's the main technique that we have. But this is when we have a common set of vertices. What happens when we don't have a common set of vertices, or the graphs are of different sizes? Then they are in a different space that we would have to compare between this graph G and this graph H, but they're of different sizes, so we cannot compare them. And that's where people in practice, what they do is they compute some graph properties, say the degree distribution of the graph. What it really does is it maps the graph into some common metric space, and then we can compare between the two graphs. But what does this really mean? I mean, this work that we have, it's not a very clear picture as we have in the common vertex assumption, but we just want to understand what is the real problem that people, I mean, or the formal problem that people in practice are solving in this scenario here. What and the argument for this is that suppose, so we are doing the comparison in this metric space. So what essentially we are comparing is, we are mapping these probability or the models or the probability distributions into this metric space. So these are our proxy targets, and it need not be a bijective map. So there can be equivalence classes between which we cannot distinguish, within which we cannot distinguish. But as long as a nice concentration happens between this network statistics and this proxy target, then we can come up with a minimax, or we can come up with a generic consistent test for this problem. And in some cases, these kind of tests, say based on the graph spectrum, can even be minimax optimal under some model assumptions, if we put some additional model assumptions. But the whole picture in this situation is still, I mean, a lot is not understood properly. So that brings me to the end of this talk. Whether, in summary, we look at both, I mean, mainly at this common vertex situation, come up with tests which are computationally efficient and which are also theoretically optimal. And in the different graph size scenario, we have something, I'm not very happy about it, but there is some argument one can make about what is the common problem. There are different things one can look at beyond the current scenario. So for example, for dealing with graphs of different sizes, a natural model would be testing between two graph types, because graphons help us in generating graphs of different sizes. But the challenge is, how do we do a vertex alignment in context of graphons? That's very unclear from the current literature. One can also look at, assuming independence of edges was one of the only assumptions that we had when we had inhomogeneous order training. Otherwise, there is no structural assumption. So, if we remove the assumption of, independence assumption, then it takes us to this whole broader picture of testing between high-dimensional discrete distributions. So, for example, one can look at the Ising model testing literature and then try to understand what would really happen if we have very small sample size, which is not understood in this literature as well. So, with that, I would end the talk.
And now is the time for questions.
So, sorry, this is possibly a very silly question, but somehow I never caught where you were actually using the fact that this was a graph. It seems like it's just a string of numbers, or two strings of numbers.
Yes. So the first one is, if we assume it's a string of numbers, the natural would be take the Frobenius norm, which doesn't really work if you have one observation. And then we don't use the fact that it's a graph, but we use the fact it's a matrix. And that really helps in solving the problem when we have unit sample size.
So if somebody presented you with this problem, or with a problem that just involved two binary sequences, and they wanted to know if these were generated, a bunch of bias coins with each with a different unknown bias, possibly, and two samples. So you could package that into a matrix and then do your test on it.
Yes.
So there's somehow nothing special about the fact the graph thing is just, your approach to why you were interested in this. Is that right?
Yes.
And was this already known in the kind of more simple context of the binary sequences? Because it seems like black magic to me that you can do this.
Yeah, so the binary sequences, again, as I mentioned here, it falls in the general problem of testing high-dimensional discrete distributions. And there is already literature on this, but from a sample complexity point of view, which says that, well, our problem is to distinguish in the total variation distance. And then we cannot do anything beyond having a linear number of observations. But what happens when we don't have that? So that's where these kind of approaches would come.
Any other questions? Yeah.
I have a question about the first part of your talk where you explained, we introduced certain estimators, and you showed that for n to infinity, so the one diverges if they're not equal, and the other has a limiting distribution. Do you need to sort of compute a threshold in order to say, for any finite n?
Yes.
Can you do that? I mean, can
yes,
you get sort of
so
large n behavior to?
So basically, when we talk about, say, the spectral norm scenario, what we know is that, assuming that the scaling matrix is known, that's the only approximate part, and it can be obtained from some sort of a block model approximation. But assuming that is known, then there is this universal versatility result by Laszlo Erdős, which says that as long as there is independence in the random matrix, we know that the limiting extreme eigenvalues are going to be tracy Witten. And we just use it and then consider the fact that it could be the maximum positive or the maximum negative eigenvalue, and that gives us a union bound. And you just, the threshold is based on the threshold for
Okay.
tracy Witten.
Thank you.
Very simple.
Okay, so let's sing it again.
Thank you.